In this video, we're going to learn how to master the fourth and final AP Physics 1 FRQ, the qualitative/quantitative translation. And so this question is just how it sounds. We're going to be asked to relate a quantitative explanation to a scenario using quantitative physics laws that govern the scenario. And so this question is only worth 8 points and recommended 15 to 20 minutes, so it's a bit shorter than the previous questions. So yeah, let's just jump in and see what they mean by that in this example. So we have a block of mass m1 slides to the right along a horizontal surface with speed v0 towards block 2 of m2, which is initially at rest shown in figure 1. Okay. When block 1 slides with block 2, they stick together. The friction between the blocks and the surface is negligible. Okay, so part A, it asks, if block 2 is much less massive than block 1, estimate the approximate speed of the two-block system after collision in terms of v0 and justify your estimate using qualitative reasoning beyond referencing equations. So we need to figure out what physics principle we're going to want to reference to explain our reasoning. And so what I'm first going to jump to here is momentum. And the reason for that is we have a collision, and we know momentum is great for collisions. In particular, we have an inelastic collision here, so we can't really use energy because energy is not conserved during inelastic collisions. And so momentum is going to be our best choice. There are other ways to do it using like Newton's third law in interactions or using center of mass velocity. But I'm going to do this question using conservation of momentum since we have no non-conservative forces. And so first we need to determine what we're actually going to say about this final velocity given v0. And so the question is saying if this m2 was really, really small relative to m1, then this v0 is going to be something related to vf. And so we can say that v0 is going to be about equal to vf. Because we can think about it, let's say this block 1 was like a truck that runs into a marble that's stationary. That v final is not going to change much compared to what it was before it hit a marble, because the mass difference is so different. And so that's basically what we want to say. And so we can say something like, since there's no non-conservative forces, the momentum initial equals the momentum final, or basically momentum is conserved. And so all of the momentum is in block 1 initially. So we can say like all the momentum is in block 1 initially. And so at the final, most of that block 2's momentum is going to be very low because it has such a low mass. And so the final momentum of block 2 is going to be very low, so most of that momentum that's conserved is coming from block 1. Or all of it's coming from block 1, but a lot of it is going to stay in block 1 or the whole system since they're becoming together. And so that's basically what we want to say. So all the momentum is block 1 initially, and then only a small amount of momentum is transferred to block 2. And so the v0 is going to be about equal to v final. Okay, so that was kind of like a bit scrappy of a response, so you would want to write an actual good paragraph, but that's the general idea. The momentum is conserved, all the momentum is in the initial block, and block 2 is not going to have much momentum compared to block 1 after the collision since the mass is so small. Okay, and so that's basically what we want to say. And so in part B it says, starting with conservation of momentum, derive an equation for v final of the two-block system in terms of the masses in the v0. And so we're starting with conservation of momentum. So we know momentum is conserved. It already tells you that, and we could actually use that in part A if we were stuck. But we know that P0 equals the P final. And so what is P0 going to be? Well, we have the two blocks in the system, which is m1, and momentum is mass times velocity, so v0, plus this m2, but the v0 of m2 is just 0 since it's stationary. Okay? And it equals m1 plus, or actually I'll write this out fully first, is this m1 is going to have a v final, and this m2 is going to have a v final. Okay? And so this just goes to 0 because it's not moving. And so we just get m1 v naught, and then we can factor out v final and get m1 plus m2 v final. And so we can write this in terms of v final, which equals m1 v naught over m1 plus m2. And that's our equation. Okay, and the last part says block 2 is much less massive than block 1. Or if block 2 is much less with block 1, does this equation agree with the reasoning we gave in part A and justify why? And so the reasoning we gave in A was that since when block 2 is much less massive, it's not going to have as much of an impact because of the momentum. And so we have to say that this equation does agree, and it should agree if we're correct on part A. And so we can show, like, if m2 is much less than m1, then we can say that m2 is about 0 in comparison. Or really what we can say is that m1 plus m2 is going to be about equal to just m1 because it's so insignificantly small. And when this happens, vf equals m1 v naught, and then if we have this just equaling m1, these m1's canceled and it equals v naught, so we get vf equals v naught. So yes, it agrees. Since like when the masses are, when mass 2 is so much smaller, so when we have this m2 much less than m1, we can say that m1 plus m2 is going to be about equal to m1, and then, like, given this expression, we can say the masses cancel and vf is about equal to v naught. And so you'd want to give kind of a paragraph response here. Okay, so now let's look at what we actually get points for in all this question. So the first point we get is simply saying that this is what holds, that the v naught is about equal to the v final. So that's the point straight up. And then for our justification, we get 1 point for connecting our claim to the main idea, which we use conservation of momentum, where we said momentum is conserved. We could also use Newton's third law or momentum of the center of mass of the system as your overall physics law that governs this interaction. But we use conservation of momentum, and I think it's the easiest to use. Okay, and then we also get a point for the justification. So for us, it would be a statement relating that the block's mass relative to the magnitude of the change of the block's momentum is very small, so the change in velocities will be insignificant. So you get a point for your justification. If you use Newton's third law, you could get a point for a correct statement relating Newton's third law to a small acceleration of block 2 or a large acceleration for block 1. And then if you use momentum of the center of mass, you could say that the center of mass of the system is not going to change. And so since the center of mass is almost all coming from that block 1, when it hits block 2, it's not going to change much, so the total velocity doesn't change, or something related to that. Okay, so that justification is the other point. And so now part B, they're giving out a lot of points for part B. Like, you get 1 point just for writing this down. You get another point for showing what, like, each of these equal, and then you get another point for your final derivation. So that's like a free 3 points right there if you know where to start, and you can just simply plug in what the momentums are of initial and final and solve for this v final, which is really nice. Okay, and so finally part D, part D had 2 points. So you first get a point for a statement addressing the functional dependence between the mass and the final speed of the 2-block system. And you don't even have to we don't even have to even use it correctly. You just have to use functional dependence. Basically means just using the equation that you drove here. So we kind of like showed that mathematically. So that's where that first point comes from. And then you also get a point for a correct justification making a link to this equation. So saying something like when the mass 2 is much less than block 1, this final speed would be about equal. And then saying, like, in the equation we derived, like the mass of, or the final speed is inversely proportional to that mass 2. So if mass 2 is very small, it's going to effectively have the masses be equal in bottom and the numerators cancel. That's what we showed right here. And so the velocity is equal, which would match what we said. And so that's it. That's all of the FRQ right there. If you didn't watch the first 3 FRQ sections, go back and watch those, because those are much different questions than this one, obviously. And so yeah, that's how you can get as many points for the FRQ. Leave your questions down in the comments, and thanks for watching.